looks like Nelson Rodriguez Faustino, the next scheduled speaker, is not here, so we're going to make a schedule change, and Francesco Toppan is going to speak now instead of at 5 as planned. So I'm pleased to introduce Francesco. He will speak about quasi-nonassociativity from an exceptional spectrum generating graph.
Okay. Thank you. Thanks the organizer. I don't need to put headphone and everything. You understand me, right? Yeah. Just
if you want to leave something for future,
working great. Okay, so perfect. Okay, so this is the title of my talk. First of all, I would like to thank the organizer, and especially Raimundo, for the opportunity to speak in this very interesting conference and environment. So it's a little bit provocative title, Quasi-nonassociativity, but it is a very well put name. I will explain that. And it is based on this paper, which has been published this year in Journal Mathematical Physics with Gianna, who is here present, and with a collaborator from Japan, Naruhiko Aizawa, that he will visit São Paulo next month, by the way. So, this is the title of my talk, and it is based on something which is recognition fact that in both in physics and in mathematics, there are some exceptional structures that are more important than the ordinary structure which are boring. I don't have much time to mention the connection in physics, but you say all the web of dualities of superstrings and theory are all based on exceptionality. There are some exceptional structures which are behind that. 10-dimensional superstrings it moves in 8-dimensional transverse space, and in 8-dimensional is the dimension of the triality. Concerning mathematics, it is very well established that you have all Lie algebras, simple Lie algebras that are classified by Cartan. You have the 4 classical series, and then there are 5 exceptional Lie algebras, and they are all here, and they are all related with the maximal division algebra, which is the division algebra of the octonions, which is non-associative, and they are related via the Freudenthal-Tisse magic square construction. If you go beyond the Lie algebra, you get the super Lie algebra, the two-graded Lie algebra. Then they have been classified by Victor Katz in the middle of the 70s. Well, it was proven, you don't have the analysis of this construction, but it was proven in 1983 by Tony Sudbury that these 2 exceptional Lie superalgebra, which are known in the literature as G3 and F4, are also described by octonions. And in my talk, I will focus on F4 exceptional Lie superalgebra. And please note that it is not the same as F4, which is the exceptional Lie algebra, which is the automorphism of the Artin algebra. And I want to mention that in physics, there existed only one truly genuine example of non-associative quantum mechanics which satisfied all axioms. And this was done in the setting of Jordan quantum mechanics. He formulated an alternative framework. Then this is passed by Jordan. This is where mathematicians took the name of Jordan or Jordan algebras from that. But there is a unique example of quantum mechanics which is not equivalent to the standard associative formulation. And this done in a finite setting. And the finite setting was described by this founding father of quantum mechanics, Jordan, von Neumann, and Wigner, in this paper in 1934, where he introduced the algebra of 3 by 3 Hermitian matrices, which are orthogonally valued, and nowadays this is called the exceptional algebra. All other examples in quantum mechanics and physics, where there is some non-associativity, including the example I give you here, the non-associativity disappears, has some remnant in some sector of the theory which is Okay, the setting I'm using is so-called conformal mechanics. And it's a well-defined theory, well-defined Hamiltonian in 1 + 1 dimension. It was introduced by Calogero in 1969. Conformal mechanics, we have potential of the type 1/x². We prove that it has an SL2 invariance. And a few years later, the Alfarov Rubin Furlan, they proved that if you introduce an oscillatorial term on this kind of theory, you have exactly the same dynamical symmetry of the theory. So you don't change the dynamical symmetry, but you have an interesting feature. Because of the oscillatorial term, it means that you have a well-defined ground state and a discrete spectrum, while conformal mechanics, in general, the spectrum is continuous. But you can go pass from one to the other just without changing the dynamical symmetry of the theory, or if you want, the spectrum generating algebra. Well, what I'm saying is based on supersymmetry, word-line supersymmetry. So, well, these are some work where we introduced the classification of word-line supersymmetry in 2001, and then these are some series of work which are preliminary, but I will just focus on the content of it. So, first of all, it is based on octonion, the largest division algebra, non-associative. Octonions are defined by this composition law. You have 7 so-called imagery octonions. They satisfy this composition law over here. And Cijk, it is a totally antisymmetric tensor. They are known as octonionic structure constant. And on the base of these, there are only 3 totally antisymmetric tensors which are compatible with the octonionic multiplication. And they are given by tensors which are rank 3, 4, and 7. And they are explicitly given here, the formula are here. The rank 7 is a Levi-Civita tensor, totally antisymmetric. The rank 4 is given by this one. And only 2, in fact, are fundamental because there exists a relation, which is given by here, that tells you that the third is always expressible in terms of 2 of them. And then you can choose which one you want. And octonions are related with a beautiful structure, which is the Fano plane, which is the simplest example of finite projective geometry, where you have 7 points, you have 7 lines, and they have duality because it's a projective geometry. 2 points uniquely determine 1 line. The intersection of 2 lines uniquely determine 1 point. And the circle is also 1 line, so you can counter that. Which is the relation of octonions and Fano plane? Well, the relation looks like that. In fact, you should also put some arrow. If you take the octonionic structure constant, which have 3 indices here, they are 0 if they do not belong to the line. Standard notation, I put 1, 2, 3, 4. 1, 2, 4 will be 0, but 1, 2, 3 will be different from 0, and you can put some arrow to make the direction because they are totally antisymmetric. 1 and 2 go to 3, and so on and so on. And this is all this how it works in these kind of cases. Okay? So this is the first relation between octonionic structure constant, rank 3, and the Fano plane. Now, octonions are non-associative, and indeed, the non-associativity of octonions is encoded in the structure constant of the octonions. How does it work? Let us take a simple example. Let us multiply E1, E2, E4 on the left in this way, with this type of parenthesis, on the right with this type of parenthesis. And if you follow the rule, E1 and E2 go to E3, but then E3 to E4, it go to E5, and E3, E4 go to E5, but it is a minus sign, and you get a minus E5. But if you go on the other way, you get E1, which multiply E2, E4. E2, E4 gives E6, 2, 4, 6 with the plus sign, and then E1 and E6 gives again E5, but the sign is plus this time. So they are non-associative due to this. The structure constant of the octonions encode the non-associativity of the octonions. But this is not a full story. Because you can, in fact, realize the octonions in this way. You take a real octonions. This is characterized by 8 real coordinates. X0 is related with the identity. And then you multiply these octonions. On the left, you have a left multiplication in terms of some image octonions, let me call EI. There are 7 of them. And this induces a new octonions, which is also real. And these new octonions will be expressed by some other combination of real numbers. I call it X prime. There are 8 of them. And these 8 real numbers will be just realized by a linear matrix. So you have something like that, where gamma I is a 8 times 8 real matrix. And since there are 7 image octonions, you have 7 of these kind of matrices. Now, of course, when you have matrices, you can just sum matrices, you can multiply of them. Everything is just associative. But you can ask, what is the remnant of the non-associativity of the octonions? And the remnant goes in this formula here. If you follow this construction, and you take the anticommutator of this matrix here, they satisfy this kind of condition, where at the right-hand side you have the identity matrices minus 2 delta ij. And this, if you are familiar with, this is the basic relation which define the generator of the Clifford algebra, and not the generic Clifford algebra, the Clifford algebra 07, which means the Euclidean Clifford algebra with 7 negative, the space of Clifford algebra is completely negative. Now, by using this construction, you can easily realize that these matrices here are again expressed by the structure constant of the octonions, because this is also related with the structure constant of the octonions. How is explicit realization? It comes from this matrix here. You have a block-black block composition. This is 1 by 1. This is 7 by 7. And this matrix here can be expressed, their entries, with the structure constant of the octonions inside this generator of the 07 Clifford algebra. And this means that you have a double role for this structure constant. And the double role is the following. On one side, you find the non-associative multiplication of the octonions, and on the other side, they enter into an associative structure, which is the matrix realization of Clifford algebra 07. This kind of double role plays a fundamental role in what I call the quasi-nonassociativity of this construction. So, how I do it? Well, at first, remind some basic fact that when you have some Clifford algebra, in this particular example realized by 8 and 8 real matrices, I can span all my chess of 64 different inequivalent real matrices in terms of the product, antisymmetric product of this Clifford algebra. You have the identity, you take 1, which is just 7 elements, you take the product of 2 of them. Of course, the order should be given by this one. So you have 7 over 2, there are 21, and you take 3 of them, you have 35. You can go also to 4, 5, and so on, but you don't get anything new by Hodge duality, and you have just the span of this way. So this gives you the basic of symmetric, antisymmetric matrices which are contained in this chest. When you need, because this system there are encoded the supersymmetry as Z2 credit structure, you need to have some operator which plays the role of fermion parity number, which discriminates between even sector and odd sector. So 0, 7 does not have this kind of structure, but you have to go to 9, 0 by creating new operator which satisfy a Clifford algebra 9, 0, and they're given by these capital gamma matrices. There are 9 of them. They satisfy by construction this kind of relation, so it's a Euclidean realization of a Clifford algebra 9, 0. One of them is diagonal, all the other are anti-diagonal. And you can do the same kind of structure as before. Now you have 16 times 16 real matrices. There are 256 possible real matrices realized that way. And you can span in the basis of totally R antisymmetric rank R tensor. This way. And you can also do something better. You can just refine this and ask which kind of this combination are block diagonal, which kind are block anti-diagonal, which are symmetric, which are anti-symmetric, and which is the total number of them, which is 256, and this is the complete list of them. And this respect to the autonomic structure, because they are scalar or vector on the autonomic indices, or tensor. Now, these objects are the building blocks for my theory. Now, I want to specialize my construction, and I specialize my construction to supersymmetric quantum mechanics. Supersymmetric quantum mechanics was introduced in the 80s by Witten, and was very much studied in the reformulation of the Atiyah-Zinger index theorem in the context of supersymmetric quantum mechanics. It requires an operator which is a Hamiltonian, and it requires an operator, in our case n equal 8, which are the square root of the Hamiltonian, q squared equal h, and by the way, they commute with the Hamiltonian and they satisfy these superalgebra here. This is the anticommutator. What is the Hamiltonian? The Hamiltonian is a standard one. Is a standard Hamiltonian is a second order differential operator in one coordinate, the space coordinate. You have a Laplacian, I have a potential. Now I ask a very specific example of theory, which is scale invariant supersymmetric quantum mechanics. Scale invariant tells me that I have this object has the same kind of dimensionality as a derivative, then it should be proportional to 1 over x squared, which is something of the type of Calogero potential, times a matrix V, and this matrix V should be, by construction, should only be real, symmetric, and constant value. Block diagonal, constant symmetric matrix. So far, so good. And now I plug the request that this should respect this kind of model I have, the autonomic structure, which means the following. I plug the most general form for the first order differential operator Q8 and Qi that satisfy the right condition to be Hermitian, block anti-diagonal, and so on, and also satisfy this kind of condition. And there are not so many choices. By simple analysis, this is the most general possibility that I have. There are some real parameter A, B, C, D, E that should be fixed to satisfy this kind of condition. And if you plug this into, let's say, Mathematica, Wolfram Mathematica, you can realize that there is only one solution, one class of solution that is given by here. And this requirement that they should be anticommutator should be 0 solve two types of solution. These are this kind of solution for this, for real parameters. So far, so good. This is not the end of the story, because we want to have is a superconformal mechanics. And superconformal mechanics is related to have some spectrum generating algebra, which in fact is not only scale invariant, but satisfy this kind of condition. You want to have a superalgebra, finitely superalgebra, which is decomposed into a 5 grading. In the top grading here, you have only one generator, which is the Hamiltonian H. In this other odd part of the algebra, you have the 8th fermionic generator, and this corresponds to the superalgebra of supersymmetric quantum mechanics. But then you want to have also a dilatation operator, which is in the 0 sector, and you want to have the conformal partner of the theory, and also some other operators which are called R-symmetry entering here, and in such a way that all these close. And there is only one operator, which is the conformal partner of the Hamiltonian. In German, it's called K, H, K, and the dilatation close the SL2 algebra, which is here. If you take the list of Lie superalgebras classified by Katz in the 70s, well, you can check it out which of these superalgebras satisfy this kind of condition to be superconformal in this sense. And for any integer value n, there are, n can go up to infinity, you have some. N equals 0, you have just SL2. N equals 1, you have an algebra which is isomorphic to OSP12 is one of the real forms, and so on and so on. I underlined which are the exceptional Lie algebra, superalgebra. All of them enter into this class of superalgebra. In particular, for n equals 8, I have F4. G3 and 4. So, okay. F4 is a particular superalgebra. Its even sector contains 24 generators, and it is decomposed into the direct sum of SL2 and SO7. So, the superconformal operator is very easy to be determined because there can be only one choice. H is the Hamiltonian, which has a dimension -2 because derivative squared. So K should have dimension +2, should be only possibility E squared, and can be only E squared times the identity. And when you know that, you can take the commutator of K with the original operator Qi, and you determine the operator Q tilde I, and then you have the operator Q tilde I, you have to close these possible anti-commutators. And you have to ensure that this is possible. Particularly, you have to ensure that there exists R-symmetry, and you have to ensure that these Q and Q tilde are in a representation of the R-symmetry. Well, this is the point. When you do that, you have a set of relations that you have to check, and for a unique value C equals -1/12, this is simply impossible. You have only one single point. In fact, there are two solutions, but the two solutions are related by similarity, by exchanging bosons and fermion Hamiltonian, up and down. There is only one unique solution. And now you have this, you can ask yourself, aha, what is the R-symmetry of this theory? And first of all, you realize that there are 7 linear constraints which are written covariantly in terms of the autonomic structure constant. They are given by this. Since you have 7 constraints, 28 minus 7, this already tells you that you have 21 linear independent generators, 21 linear independent already identified as SO7, which is the R-symmetry of F4. The closure is guaranteed by this kind of construction here. In particular, the SO7 generator explicitly expressed in terms of the structure constant of the octonions 3, 4, rank 10 is given by this kind of relation here. All this can be checked explicitly using Mathematica. And moreover, important point, by construction, the grading Jacobi identities are satisfied despite the fact that these are structure constant of the octonions, these are non-associative. Okay, so far so good. Now, what is the kind of theory? If you want to have a theory which is an oscillator, the dynamical symmetry is preserved if you add the Hamiltonian with the K operator. The K operator is just this oscillator part, and you have something like this. And you have this oscillator plus a term which is a calogero. I will come back later on that because this is quite important. And you can solve this theory in terms of creation annihilation operator of this way. And when you do do that, you can ask A and A dagger. You can prove that these A dagger create states of energy plus 1 in terms of these Hamiltonian, and this destroy the state. You can define your lowest weight representations, which means the lowest weight representations that are annihilated, but at least one of these 8 operators here. There are 24 of these kind of states. You can reconstruct the possible lowest weight representation of these. And then, since this is not enough in order to have a Hilbert space, because this vector space should be also normalized in order to have a Hilbert space, to have a norm, then you have to ask which kind of conditions are satisfied, and you can end up with the total energy of this system. So this is how required, for instance, that the state should be normalized as a square integral function. The sextuple of square integral function on the line from minus infinity to infinity, and this is the condition. This should be should be a number, should be a real number less than infinity, which means that the power here should be greater than minus 1 half in order to get this kind of relation, and so on. So once you do that, you can describe the spectrum of the theory. You have very nice formula. We don't have time much to enter. And then you can compute the spectrum of the theory, and this gives you the following kind of structure. We have chalks.
Over there.
Oh, yeah. So, and I can prove the following. This system has 1, 2, 3, 4, 5, 6, 7 states of the ground state. 1, 2, 3, 4, 5, 6, 7, 8 states on the first excited level, 8 states on the second excited level, and so forth, and so forth. 7, 8, 8, 8. And go this way. The energy level here, which is the lowest weight, is 2/3, 5/3, 8/3, etc., etc. And they satisfy some algebra, which is called soft supersymmetry algebra. We'll explain you why. We'll give you some transparency later, how does it mean. But before doing that, I want to mention this feature of the quasi-nonassociativity with this formula, which is quite beautiful. So we have computed the theory, and the theory just has this kind of expression. This Hamiltonian here, which is uniquely determined by this term and this B, which is just a diagonal matrix proportional to 1a squared. This is just a constant. Now, let us compute this constant, and what you get is this strange bunch of numbers. Where do the heck they come from, this number? One point is the following. The supertrace of this is 0. 91, you have +7, -5. This is the even sector, and then the odd sector is 8 times 7, this is a minus, this is given, 0. That is quite expected because it's a supersymmetry, supertrace. But still you have some puzzle. Why 91, why -5, and so on. So, and this is a beautiful formula, even by here. This number here, this diagonal matrix, is explicitly expressed in terms of the octonionic structure constant in this formula on the right-hand side. And you should note that the octonionic structure constant enter twice this formula. Enter explicitly here, is Cijk, Cilmn, but also enter implicitly inside the gamma matrices, because I explained you before that the gamma matrices are explicitly written in terms of the structure constant of the photons. And they concode it in such a way to give only this kind of value here. So this is the feature of the quasi-nonassociativity, which tells you the following. You have a structure, you have a quantum mechanic which is perfectly associative. You have in principle a moduli space of all possible coupling constant of the theory. And in this particular example, only one point inside of the moduli space of this admissible coupling constant is determined by the non-associative structure of the octonions, and it is determined by the fact that this system has an F4 in exceptional spectrum generating superalgebra, which will determine the spectrum of the system. And concerning then these kind of, I have to skip a little bit, but I go this kind of point. Let me just give you here, because this gives an example. How to make this kind of spectrum generating act is in the following way. I have 8 operators, which are 8 creation of operator that they go this way for 8 different colors. I have some problem here to have 8 different colors, so I give you the example of 2 colors. Here you go this way, and you go this way, but you have to think about this way, the system, and so on and so. But you think that all these are related by one of other colors. So you have 8 different colors, and then all these reconstruct this theory in this way. And what is this kind of algebra here, which reconstructs this theory? It is some sort of supersymmetry algebra. How? Let me take this example. Take one dot here. You get a black operator twice, and you end up here. You get a red operator twice, and you end up in the same point. This is exactly the operation of supersymmetry. Q squared equals something. Then if you take the black operator and the red operator, you end up here. Why this is a dashed line? Because there is a minus sign. So, okay. You end up in this point, but with a minus sign, black and red. But if you apply on the reverse order, first red and then black, you end up in the same point, but with a plus sign. So they annihilate. So this is the supersymmetry encoded. But this is not the standard supersymmetry. Why? Because in the standard supersymmetry, it is related with some Qi, Qj, which close Q squared equal H. And H is a Hamiltonian of the theory. H is a Hermitian operator. In this example, these operators that do this game are not the Hermitian operator, they are raising operator. So this operator here realizes a supersymmetry, but the closure of this raising operator, let's say a data square, is on Z, and Z is different from H. This kind of example we call soft supersymmetry. It's an implementation of the same type of algebra as supersymmetry, but in a different context where you do not have supersymmetry in the usual context of the theory. And this is some general framework of the theory. There are some very beautiful examples, for instance, how to encode in the triangular numbers of the Greeks supersymmetry in this way. This is also the, okay, if someone will discuss with this is the also the spectrum of two-dimensional bosonic harmonic oscillator, which can be covered with this kind of supersymmetric carpet this way, and so and so. And also some other important point, but I think that it is enough for me to stop here. And please ask me question. I will be here around. So coffee break everywhere.
Any question for Francesco?
So why do you call it solid?
Because it is not a normal, this is not ordinary supersymmetry. That is one point, which is very important. And people do not much realize that. You see, when you have supersymmetry, in the original sense of the word, or supersymmetric in theory, or even in the sense by Witten, you ask for supersymmetry in such way. You have some operator, Qi, Qj, equal mu, equal delta Ij, H, tells you something that for this kind of theory, at least not in the ground state, but all in the other state, you have some degeneracy, equal number of bosons, and equal number of Fourier states. Okay? But my claim is the following, not the claim, it's the proof. You have some systems which are more general than that, where supersymmetry is encoded, but in a hidden form, because you don't realize, because do not have these kind of features of degeneracy of bosons and Fermion states. Why? Because this operator close, but close on some Z, and Z is not a Hamiltonian of the theory. In this example, Z is the raising operator. But you can use the same kind of method of supersymmetry to solve this theory. That is why you call it soft.
called soft. Sometimes actually the opposite case when Q would act horizontally.
Because it's there is an ordinary supersymmetry and this is non-ordinary. So it depends. So we found that the soft way of coding is a good way. So, okay, that's why we call it. But one can have some other name, but the point is that these kind of features, which in fact enlarge enormously the possibility to use supersymmetry, even to theory which are non supersymmetric, which doesn't have this kind of degeneracy.
Francesco, just one question about that Jacobi identity that you said, because you have something like 64 ways to compute all these products in non-associative way. So how do you know really that the Jacobi identity works for all these cases? Do you have something stronger than a plain computation, or?
Of course, okay. I mean, it is enough to you can prove it explicitly by computation. Of course, that the Jacobi identity are satisfied, but of course they are satisfied by construction because these are just operators. They are differential operator, matrix differential operator. Matrix differential operator, you don't even need to do it, but they satisfy the Jacobi identity.
You realize that's matrices?
Yeah. You see, there is one point.
Non-associative.
No, the non-associativity is encoded inside this matrix. That is the point. You have this information between by exceptionality, the octonions. Octonions only give information about some exceptional structure, like exceptional algebra, exceptional superalgebra. Okay. You can also work this theory in much more complicated way without realizing that there is this octonial structure behind. But this simplifies a lot and in practical tells you that you don't have anything but this kind of system. That is the point. So the information about non-associativity is not on the level of the dynamics. It is on the level you can call of the metadynamics. It is on the level of the moduli space which are admissible by your theory. Only special, in this case, only a single point in the moduli space is related with this non-associative structure. That's
A single one.
The model is completely unique, which is just a F4. It's absolutely exceptional in this sense. I have some other comment about non-associativity in physics. There are at least other cases. For instance, people use, number brackets. They use quasi-triangular of algebra. They use some non-associative structure there. There is non-associative structure. But in such case, you don't need them. Why? Because in this case, you have some non-associativity, which you have some cocycle. Okay? That's a non-associative cocycle. They produce some phases. These phases are non-trivial, so they are non-associative on the vector space. But quantum mechanics is not a vector space. Observable requires Ray vector space. And you lose that in that. So there are a lot of examples of non-associative structure which end up in associative system. The unique case that I know that has not been studied further is Albert algebra. In 1934, Pascal Jordan, von Neumann, and Wigner produced this model They even tried to figure out if they could reproduce the spectrum of nuclei using this model. But they didn't find anything interesting. And so this model is really a point-like model, which is algebra. It's the only consistent non-associative model so far that I know.
Yes, okay, there is ABJM. I have this theory. I don't know if you consider it physics more than Jordan. So there is a realization in terms of membranes that people work on that. But
You need to satisfy axioms. Jordan axioms tells you that this theory is consistent even if it is non-associative. If you do not have a properly defined set of axioms, so you can make a non-associative structure, but you don't know if they are consistent in the, so this, there is some work has to be done.
consistent in what sense?
As a quantum mechanical system. As a quantum mechanical system.
Let's thank Francesco again. Next speaker is Maria. That was the last speaker for the day. So
we start tomorrow with you.
we can adjourn to tomorrow. You should talk to the organizers. Raimundo and Slava.
Yeah. So you're also tight on the time to go back.
I stay here.
You're staying here a month. So perhaps we can trade if you don't find another one.
Why? Just to change my.
Well, because he might miss his flight. He's worried about.
But I guess there will be some missing speakers.
That's nice. So I'm not really sure if the guys from Morocco came. So that's the question. Okay. Sure. We can ask. I'll find out today actually if they came or not.
Sure. If you need to change,
Tomorrow. It's
What's your time?
no.
Thank you.
Saturday. Jandira sent out an email where we're staying. Oh, she sent out an email with recommendations for dinner, but I think she made reservations for speakers. But I'm sure Slava is going to do this.
Okay, then I'll see you tomorrow.
No, but the guys that are missing today are from here. Are from, like, one guy is from ICTP-SAIFR. And they confirmed that they were coming. It's one of these barbecue, so you can eat barbecue, which is called Bohemian's restaurant. It sounds like, yeah, like a lot of pizza, which is not your. There's a lot of salad. Francesco, did they come? Francesco might know the time because he's just asked for Zana. Zana, do you know the time of tomorrow's dinner? Do you know the time of tomorrow's dinner? Or when the reservations are? No, yes, Francesco just arranged that. I don't want to interrupt Francesco. Francesco found out the time. But yeah, so tomorrow early, I think, reservation for Saturday, it's basically From Sao Paulo.